I'm Jean-Luc. Wait, where's the pointer on this? It's this one. No. It's the top? Oh, yeah, the one that says pointer. Okay. So I'm going to be telling you about hagfish. Just a quick note for those of you who are into running. Yesterday we had the first running club, and it was just David and I. So today we decided that because there was nobody at 5 miles, maybe if we ran 10 miles, there would be more people interested because maybe it wasn't serious. It's because we have the afternoon off, but we'll take it very slowly and run to Fen Ditton along the Thames and maybe even stop for a pint at the Plough, which is a beautiful pub over there, and then try to run back.
You didn't mean the Thames.
Sorry, the Thames, the Cam. Whatever river is here. Okay, so this is joint work with Randy Ewald. This is work that we started on a few years ago, and it's a little bit stalled, which is why I think it's good for me to give this talk here, because perhaps people here will have big ideas on how we can unstuck it. But I think stalled or not stalled, I think it's kind of interesting, the direction that we took. So I'm going to be telling you about hagfish. A hagfish is a wonderful fish. It's a kind of eel-like looking fish. It's a kind of ancient organism. It has no teeth. It has like a sandpaper mouth, and it kind of like kills you by rubbing you to death, basically. And it's a scavenger, so it lives at the bottom of the shallow ocean, and it just kind of like eats carcasses of dead tuna and dead whales. It's about 50 centimeters long. There's quite a few species. It is not at all rare. It's kind of all over the place in the world. And it burrows into the carcass, and they can actually feed through their own skin. Like I said, they rasp at their mouth, but they actually absorb nutrients through the skins. They really are a strange, peculiar organism. And people have been fascinated with hagfish for a while, and in fact, the most fascinating thing about the hagfish is their secretion of slime. So this is a movie. For a long time, it wasn't actually known why they secreted this slime. There was a lot of controversy until about, I would say, 15 years ago, when they were filmed in is it called in vivo? What's the name when you're in the real world? In Attenborough. So here's a shark, and the shark is kind of like, now notice that the hagfish is particularly undisturbed by the presence of a shark, right? I mean, if I was a hagfish, even though I had a pretty good defense mechanism, I might start getting nervous at this point. But the hagfish is like, la, 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 la. And watch what happens. So the shark bites down, and immediately the shark recoils because its mouth is totally clogged with slime. Almost instantly. And in fact, sometimes the sharks die because it clogs their gills, and they don't survive this. Here it is in slow motion. It's amazing. It doesn't even have time to break the skin, and it's got a mouthful of slime. Okay, so there follows a sequence of videos which all kind of look similar to this one, so probably I won't show all of them, but you get the general idea. The surprising fact is just how rapid this all happens, right? So clearly, it must be activated somehow by something happening in the vicinity of the glands, which are all over the body of the hagfish. Maybe there's one now. There's some other ones that look very similar later on. The hagfish is also famous for its knotting behavior, so it can actually pass a knot through its entire body. So here's a little video on YouTube of like the wonderful world of hagfishes. Maybe I should have hooked up the sound. So when fishermen pull these things out, it just makes buckets of slime in the oh, this is crabs, but there it is. So it's just slime-orama. Delicious hagfish. Yeah, so that you can see the slime. Yeah. And here's a knot. So they think the knot is so that it clears the slime off its body by running the knot down its length.
Does it always tie the same knot, or does it?
Yeah, it only knows one knot. I'm not sure about the chirality, but it only knows. It's not right before lunch. There is that advantage that it's not the talk just before lunch. Wait. Okay. So this is the knotting behavior, which I find interesting. Also, in the lab, you can study this kind of the gel that it makes, the slime. So people have done lots of experiments on this. So here's just to show you just how much mileage you can get out of like a little bit of this. So they take a little bit of the slime. They put it in a water beaker, distilled water. Mix it. The mixing is important. And then he mixes it some more. And it's like a big sheet. Notice there's almost no water left in the thing once he does this, right? So basically, a few drops of this turn the entire beaker into slime. So it's whatever it is, it's a very kind of efficient mechanism at turning water into slime, essentially. In fact, there was a great event that you may have heard of last year. I guess some kind of a hagfish researcher was cruising around the Oregon highway and had an accident, and the impact was not good news. This is the road afterwards. Yeah, this is not good. Not good. I think this was last year or something. This was fairly recent. Okay, so let's examine what's inside the slime. So the amount of thread skein in the slime, skein. The amount of skein. Okay. Well, let me tell you first that there is thread skein. So the whole basis of this is these little balls of twine that I'm going to show you a bit more clearly in a slide. They're about 100 microns in diameter, and they constitute, when the thing is expanded, they constitute 0.002%, I believe I mean by volume of the final thing. And then there's also some mucins in there, which are these little blobs. And then finally, the rest of it is 99.996% seawater. In other words, this thing is all seawater, essentially, with these kind of threads running through it, and the threads will arise from the skeins unraveling, hence the title of my talk. So this is from Doug Fudge's group at Guelph. He's the big expert on the hagfish. So this is a micrograph of these skeins, and they really look like amazing little balls of twine, right? I mean, you could not carefully wrap thread better than this if you tried, essentially. So this is tiny. A skein consists of the thread rolled tightly packed into a ball. The skeins themselves are about 1/10 of a millimeter, but the length of thread in such one of these skeins is 15 centimeters in one of them. So there's an awful lot of thread packed into this skein. So the packing fraction is actually very close to 1 if you calculate it. So there's not much wasted space in this skein. And once it unravels, it makes a kind of network of threads, which is what gives the gel-like properties of the slime, right? So all these threads are sort of roughly aligned, but they're also entwined to some degree because of the action of the water, which mixes this all up and creates the network. But in this talk, I will focus on the actual unraveling part, not on what the network is afterwards and what gives it its properties. So not on the actual rheology of the slime. That's a hard problem. So the network itself would determine the rheology. So how viscoelastic is it, how viscous it is, etc. We can see the properties, we can understand a little bit better how this works by looking at a movie that Randy did. He happened to get a skein got stuck on a slide at one point. Oh, hi, David. Turns off internet. Okay. Come on, go away. Go away. Social media. So, let me play the movie again, maybe. But so, oh, it is playing again. So, the problem is, again, it's one of these contrast things. The thread here is pretty thin. You can barely see it. So what Randy is doing is pulling on the thread, and you can see the thing unraveling gradually. So it isn't quite wrapped up tightly as much as you might think from the previous picture. Sometimes it comes out in clumps because maybe it's tight for a while, and then maybe for a while it's a little bit more locally wrapped or something. So it's not as ordered as it might seem. Sometimes it does come out in clumps. But we'll kind of model it as if it's relatively well ordered. You can see it a bit better here. Yeah, sometimes it comes out in little clumps when you pull on it. So the modeling that I'm going to do is going to be based on a paper that I found about triboluminescence, which is the fact that chemical bindings, when broken, chemical bonds can make light. So this is a paper where they took a piece of tape, like a roll of tape, and they unrolled it very, very fast. And if you unroll it fast enough, it creates light. Did you know that? That you could use a roll of tape to light your way out, you know. I'm not sure if it's any tape. Probably if you pull on it fast enough, you can use any tape, I would suspect, because it's going to be breaking the chemical bonds, and you have to do it fast enough. In fact, in this paper, they actually rolled it fast enough to get X-rays, and they proved this by imaging their hand, you know, with the X-rays. So, yeah, tape is more powerful than you might have thought. So this is from Corte and etc. a few years ago. What I took from this paper is the kind of general model of peeling. So I want to model the peeling off of the skeins, of the thread from the skein, and so I need some kind of way of representing the peeling process. And there's a rather simple form in their paper, which is a work energy theorem that originally comes from the paper of Hong and Yue, where you write the rate of change in total energy of the system, so this is of the tape system, and T is the force drawing out the thread, and then there's a velocity-dependent peeling force, F naught of V. Okay, so the model is to write a formula like this, but in fact, you can make an even simpler model when you say that the elastic energy of the tape doesn't change. So the tape is actually not stretchy. You're just merely peeling it off, but you neglect the actual elastic energy of the tape, so that you say that U dot is 0, in which case it's just a balance between the force drawing out the thread and this, well, imposed velocity-dependent peeling force. So in other words, the tension in the thread is going to be equal to the peeling force that you're pulling on it, and this is just some phenomenological law that you need to invent or model depending by observations. I mean, because this is a sticky process, right? It isn't easy to derive something from first principles. You kind of have to use phenomenological models, and in fact, the simplest models that people use for a peeling force is something which is some power of the velocity, where m is some index between 0 and 1. In other words, the force needed to peel off scales with the velocity, so the faster I try to pull, the harder I have to pull. Yes?
Good question. So, is it for surely known that this thread wraps around like a...
No, I said it doesn't. I said it doesn't, right? It comes out in clumps sometimes.
Yeah, but maybe it's all just, you know, there's a zigzag and it's... You can maybe pull on both ends and it will just unravel rather than...
Yeah, but there would still be an adhesion force, right, to the whole thing. So that's right. This doesn't really see the mechanism of rolling very much, right? It's just the adhesion modeling. But clearly it doesn't unravel all in one go when Randy was pulling on it, you know, from one thread, right? It would come out in clumps.
Interaction with a lot of water could be different.
It was already in water, right, when he was doing this. Yeah. So the peeling velocity given the tension is just the inverse of this, is 1 over m. And so that you can write that the total length of thread drawn out satisfies this, a law like this, right? The rate of change of the length that you've drawn out is the force divided by some constant and some power. So, but you also need to conserve mass, meaning as I draw thread out of this skein, I need to account for the fact that the skein is shrinking. I'm going to take a spherical skein, or yeah, a spherical skein, because it is spherical. So I'm not being very careful about exactly how it's packed, but it is roughly a little ball, not a cylinder. And so therefore I'll model it like a sphere. So the volume of the sphere plus the volume of the thread that I've extruded, where r is the radius of the thread, should be constant. And so I get a relationship between the rate of change of the length of the thread that I've drawn out versus the change in the radius of the skein, where eta here is a packing fraction, right? So there may be some inefficiency in packing, but as I said, it's going to be basically 1, right? So I'm going to set it to 1 in most calculations. So under constant tension, you can easily solve for the depletion time, the time it takes you to empty the roll of tape, and you get a formula like this, right? Given some initial radius, you run out at this infinite time, of course. So there's no fluid yet, so let's put a little bit of fluid dynamics. What I would like to do is model the unraveling in a fluid dynamical way, just to see how quickly a fluid flow can unravel one of these skeins. Okay? So to model the effect of the fluid on the thread, we go to resistive force theory. So we're going to have a long, dangly thread coming out of our little ball-shaped skein, and so we write down the force balance and the torque balance from resistive force theory, and so it's the standard equations where x is the position of the thread, s is the arc length, delta is the slenderness parameter that I'll define in a second. It's the log of the thickness in some sense, or 1 over log in the thickness. T is the tension, etc. U is going to be viscosity of the flow. So, here's a lot of what I just said. Now, what's important is that we need to be careful about Eulerian and Lagrangian labels in this, because as we unravel the skein, we're creating new thread that wasn't there before in our coordinates. So in other words, we're using resistive force theory to model a length of thread, but that length of thread is lengthening. So we need to be careful about which fluid, which thread elements are where. And so labeling things converting between Lagrangian and Eulerian labels is actually important in this case to do it properly. And here delta, as I said, is a slenderness parameter that usually shows up in resistive force theory. So it's 1 over the log of the thickness, basically. Okay. So all of these will be assumed small, of course, because the aspect ratio of the thread is going to be rather large. Right? The thread is much longer than it is wide. And there's a way to add a non-local term to all of this, which takes into account the bending of the thread. But mostly I'm going to be dealing with straight threads here, just for modeling purposes. But you could add the non-local term to this to make it into slender body. To make it to slender body theory. So let's do a very simple case first. So assume the skein is immersed in a one-dimensional flow, okay? And you're examining everything in the neighborhood of the origin. The thread remains straight and aligned with the horizontal. So in other words, unidirectional flow, and therefore there's no reason for my skein to start bending. So therefore it's just linear. The resistive force theory then simplifies greatly, and you just get these two equations because there's no curvature, basically. And all you need to do is tell me some boundary conditions that you put at the ends of the skein. And here I'm going to do two types of experiments involving different boundary conditions. So the unraveling will look something like this. I mentioned at the beginning that you had to be careful between Lagrangian and Eulerian labels. So S is really a Lagrangian label because it remembers kind of where it was initially. What's happening is that you're adding thread as you go along. So L0 is the initial length of thread that you had. And then later on you'll have length L of extruded thread. So this arc length parameter is in S. So that's the initial piece of thread. And you add by unraveling in this section. Okay, so let's first tether our skein. So meaning I anchor the skein, much like Randy was doing in the experiment that I shown, where the skein was stuck to the slide, basically, and he was pulling on it. But in this case, the skein is stuck to something, and I'm letting a flow come past. Okay, so hydrodynamics are going to unravel the skein, and so you apply the boundary conditions now that there's a free end to the thread, and there's a tethered end, which I'm keeping at a fixed position, capital X. Okay? And so you need one more boundary condition that you can get from the force balance equation and doing a kind of kinematic constraint about the way the endpoint moves, or as you extrude the thread, right? So you just take a time derivative of the fact that this point should remain motionless in the Eulerian coordinates, and so therefore this is 0, and you get this kind of kinematic constraint, and you obtain a value for the derivative of the force at the end. And so you can solve this after some manipulation of the equation, then using this Peeling force law, you get a nice ordinary differential equation. It's a funny differential equation just because there's this fractional exponent in the time derivative, but that's not a big problem. And u bar of x here is actually just the thread average velocity, right? Because you're averaging it over this anchor point, and L is how much thread you've drawn out so far. So in other words, the thread is feeling the flow, right, which is what's causing it to get peeled off. And so the total force on the thread is proportional to how much thread has been extruded so far. Okay? So it's the thread average velocity. So that makes perfect sense. Okay? So you just need to solve this ODE. It's an integral equation because of this averaging of the velocity over the thread. Okay? And so you can't solve it analytically except in some asymptotic limits for special choices of m, but it doesn't matter. It's dead easy to solve numerically, and you get something like this. You get that if you take an extensional flow, which I'm going to, I'm taking kind of rheology viewpoint here, which means I take simple flows to see the behavior of the skein. So, in rheology, a very standard flow is to take extensional flow, so having something which is linear in x, basically, and you apply this flow, and you see what happens to the length as a function of time, and you can see the length starts out at some initial condition where it's small, it grows, and then there's a finite time singularity where the drag on the thread, because it's come out to a certain length, suddenly kind of explodes, and now you unravel the whole thing near the end. Okay, so the thing gets unraveled rather suddenly when you're holding it like this. Okay? Once it gets long enough. So in other words, there's a big transient, right? But eventually it kind of explodes out. So if you look, this is the radius of the skein as a function of time. So the radius barely changes when suddenly almost all the thread comes out all of a sudden when it's long enough. So it kind of really catastrophically comes out of the skein.
What m is this?
Sorry?
What's the m, the exponent?
I don't remember which m I used actually for this. Yeah. But this, later on I'll have some more specific parameters because this is not the most interesting case. So I didn't really try to plug in physical parameters. The next one I'll be more physical because it's not actually tethered in the actual, slime. Okay. So the more relevant case, which is harder to treat but more interesting, is the free skein. So now the skein is no longer tethered at the origin. I'm letting it go through the fluid. And so now what determines whether thread comes out is the differential force between the drag force on the ball, which is the skein, and the drag force on the thread that's come out. Okay? So, in other words, in a constant flow, these would just be advected along and thread would never come out. So there needs to be a velocity gradient to create a difference in drag between these two things so that there'll be some peeling out of the thread. Okay? So now that means that at one end of the thread, the boundary condition we put is that the tension force is the drag force on a sphere of radius r, where r is the current radius of our skein, and proportional to the difference in velocity, the local velocity minus the skein velocity. Okay, so the boundary condition that we had before, which was in this case the tethered boundary condition, gets replaced by this kind of Stokes drag law for a sphere condition on the force on the thread. Okay, and the other end, of course, is free again, like in the previous case, at s equals 0. So s equals 0 is the free end, and s equals L is the sphere end. Okay? And so the Eulerian position of a thread element now, because now the whole thing moves, right? Beforehand, I had it tethered at 0 and it was extending, but now there's actually, the whole thing moves in some frame, and so you have to be careful how you define your coordinates. So now this kind of center position of the whole thing is something that can actually depend on time, right? That's the position of the skein. So that was a constant before, but now it's allowed to vary in time. Okay? And so again, you can write down an equation for this. And again, it becomes more complicated now because you've got, again, your m coming from your peeling law, but now there's also an L dot coming from the movement of the skein, basically, right? So there's extra time derivatives. So this is more akin to a differential algebraic equation now, because in principle, you can't necessarily solve for L dot in closed form, depending on what m is, right? There's no exact solution for L dot. So you must be a bit careful about solution branches of this solution as a differential algebraic equation. But nothing funny happens here. If I start on the correct branch, I remain on the correct branch. So there's no strange behavior that you get in differential algebraic equations sometimes. By the way, this kind of behavior is also seen in the tape problem. So the tape problem also has differential algebraic equations like this. And what these lead to is they lead to phenomena like hysteresis and things like that. So in other words, history dependence, which moves you from different solution branches of the differential algebraic equation. But here, because I'm not trying to retract the thread or anything like that, there's nothing bizarre. This is not yet a closed system. We need a separate equation for x dot, and that's where resistive force theory comes in. And again, I'm skipping a lot of the algebraic details because I've already shown you quite a bit of them along the way. So eventually, we now get a system of two differential equations. One of them is similar to what I had before. It basically says, it's for the length, the rate of change of the length of the thread with this power m that comes from modeling. And then there's also added an equation for the position of the skein itself, which depends on the change of length of thread and the difference between the local velocity minus this thing, which is not quite the integrated velocity over the thread. It kind of allows for this, well, I'm not sure that I have good intuition exactly why it shows up in this form, right? There's a lot going on here. This is basically you're trying to evaluate the velocity at this point, capital X, and you have to take its non-local difference between velocities at positions little x and integrate over the whole thread. I'm not sure that I have a good hand-wavy explanation as to why exactly this kind of term shows up, but that's basically the non-local averaging over the thread now takes this form if the thing is allowed to move freely and extend as I described. So, and again, R and L at the end of the day have to be related by mass conservation. So notice that I'm mixing R and L's, but these are again related by the mass conservation equation for the total mass. So again, this is, as an ODE, it's a kind of not an easy system, but it's still not hard to solve numerically. And so you just place this in MATLAB, and you, it simplifies particularly nicely when you have a extensional flow. So taking a constant flow would be useless. Taking a uniform flow would be useless because the whole system would just translate as a solid body in a way. So you have to take some velocity gradients for the thing to actually extend. And so you take an extensional flow, and you can reduce all the equations together now as to a one ODE. So this is much nicer. But again, it's not a particularly nice ODE. It's a L squared over L kind of form. So it's a rational ODE. But it's not hard to solve. Okay. So there are some asymptotic limits where you can say something, but I'm going to choose instead to solve this analytically, solve this numerically. Okay. So here's a numerical solution for what the extensional flow looks like now. And now I have more parameters. Shreyas was asking about the values of things. A lot of the values for the parameters I had to guess at. And this is one problem with the analysis, is that I don't really know what the parameters for the hagfish slime are. So a lot of these are guesstimates based on, of all things, the tape problem, right? In the sense that I don't know what the chemical binding strength is of the peeling force. So I just took it as if it was an extremely narrow piece of tape, right? So I took the limit as the macroscopic tape went to the size of the hagfish, thread or tape. But for all I know, it could be 5 orders of magnitude larger or smaller than this. So I don't have much control over what these values should be. I was hoping maybe an experiment could be designed to do this, but it hasn't really happened yet with Randy. But other values are pretty well pinned down, meaning the radius of the thread is about 1 micron, the initial radius of the skein is about 50 micron, and then the initial length that you start with, that you can just use any number you want. That's the amount by which the little thread dangles out initially from the skein. So that'll vary from skein to skein. It's a kind of random number. Viscosity, this exponent, again, this comes from the tape case. In their paper, they had an exponent of about 1/3, and I figure why not use that, because I don't really know what number to use for the hagfish anyways. And similarly for this peeling force. The packing fraction is 1, because as I said, it's very close to 1. And I'm taking an extensional flow of 1 inverse second, a rate of strain of 1 inverse second, just because that's a good ballpark parameter for the kind of turbulent values you would get for the rate of strain in the presence of the kind of flow velocities that you see for the hagfish. And so you get a curve like this, where as a function of time, the length of the extrude thread now grows actually more rapidly initially, but it doesn't show an explosion, a finite time explosion, as it did in the previous case. And the reason because as you get more and more drawn out, you're shrinking the size of the sphere, and so things are getting worse and worse and worse for you, right? So at first it's easier to extrude well, at first it's not necessarily easier because you also don't have that much thread, right? But the sphere is bigger. But then as you get more thread, you might think, aha, I have more drag, so things are helping, but the sphere is getting smaller because you're drawing out the thread. And so there's a kind of slow regime, and then you get a good growth rate, but then eventually you run out. This is actually not a numerical error. You know, I didn't choose to stop. This is when you actually run out of skein. There's a finite time where you actually do eventually reach the 0 point, which you might imagine, by the way, that it doesn't have to happen, right? You could get a mathematical model which asymptotes to 0 skein, but doesn't actually achieve it in finite time. But I think because of the exponent m equals to 1/3, you actually do achieve an empty skein in finite time. So that at least is sensible. The skein does unravel. But there's a problem. Can anybody spot the problem in this slide?
10,000 seconds.
Exactly, right? The parameters that I guesstimated at, as I said, from looking at those papers, and again, the first row of numbers I'm pretty happy with, right? It's these two numbers, m equals 1/3, I'm pretty sure that doesn't affect things so much, but it's this peeling force that I really have, or scale, you know, I guess it's peeling force to the minus 1/3. It's not a peeling force, right? It's force divided by velocity to minus 1/3, or velocity to the minus m, right? This number, I just have no idea what to put. I suppose I could go back now and divide this by, or sort of multiply this by 10,000, and then it would match perfectly. Because the goal will be to achieve this within like 1 second, right? Because that's what the hagfish is clearly doing. So the point is that even though I think this is a nice model, I'm not so sure it's actually the correct model for this phenomenon. It's a nice model for something, but until I can convince myself of what dimensional number to put here, it's hard to say that this is actually what's happening in the hagfish. So some experiment would be needed to do the peeling, which is kind of harder to do than you might think. I mean, I can't do it. I don't have any hagfish. After that big accident I had, I lost all my hagfish. Hopefully Randy can do this experiment eventually, but he might have had his attention drifted to other problems by now. Hopefully I can get him to refocus. So you can see that it's less dramatic, right? It's less sharp a transition than before. But I think it's still a model that predicts some nice characteristics of how this ball of twine would unravel. So these are the same conclusions that I just told you, but written down. So the depletion time here is about 3 hours, so that's not correct, right? From the point of view of what we see in the real world. So the problem is that I have no real idea how to fix that number, and maybe scaling it down from the tape was not the right thing to do. Also, the drag force may change a lot if the filament starts to undulate, right? So that may change the characteristics of the problem also. So maybe assuming that the thread remains relatively straight is not a very good assumption. And then the final thing is the damn mucins. You'll notice that if you read papers in the literature, it seems to me that whenever you don't know what's happening, you say, but there are mucins, and we don't understand their role. So mucins seem to be I call them the dark matter of these kinds of hagfish problems, because you can sort of absorb any ill understood behavior into the mucins. So they say, well, it must be the mucins. But they're kind of too small to properly measure, etc. Because they soak up water. They're like hydrogels a bit, right? They soak up water and they swell. So maybe that this swelling has something to do, sort of catalyzes the extension by sticking to the thread or something like that. But I have not seen anybody observe this in an experiment, and therefore it's really hard to make a model. So I think the conclusion is that this zeroth order model is not yet particularly successful. I'm not confident that this actually explains the behavior, which is why we actually haven't published this after several years. So hopefully some experiments on the way. Thank you very much.
Yeah. Jean-Luc, this is very much like the DNA packing in the viral capsids. you have almost crystalline density,
Uh-huh.
and the DNA is no duplex DNA, so it's fairly stiff. So you've got the stiffness of the DNA is packed in at 6 to 10 atmospheres, and then that drives the ejection.
Yeah, but it's not, there's nothing holding the sky. The sky is not just crystallized, right?
Feed
Because
each other, I guess that's it.
yeah, but it lives in water. It lives, you know. It's hard to see why it doesn't just spontaneously always unravel, right? It's not held in a cell or something like that, in a nucleus.
It's got to be just sticking to itself.
Exactly, it's sticking to
How
itself.
stiff is it?
I don't know, but I don't. I'm not. This is much bigger than DNA molecules, right? So I think it's nowhere near as stiff as DNA.
I have two questions. One, what's the sensitivity of the result to M? You suggested that it's not very sensitive to M. My intuition is the opposite.
Yeah.
But that's one question.
I think that, yeah, you're right. I think especially as you go towards 0 or 1, then things are. If you set m equal to 1, I think it actually takes forever to unravel. Yeah. So you're right. I probably lied a little bit. I think what I mean is that ballpark in the middle m range, you know, a half, a third, it doesn't depend too much, but you probably want to stay away from the edges. You get very pathological behavior.
My second question, is it possible that the force, the tension,
Yeah.
is actually time dependent, because it's not really like peeling tape from a scotch tape.
Yes, I think so. Yeah, absolutely. The point was just to try to make the simplest thing, but you're perfectly right. There must be other effects. It's just in the absence of some good experiments, it's really hard to just guess at things. You know, I could probably get anything I want by modifying enough things, right? So I'm a bit reluctant to do that. Yeah.
In turbulence, there is a dramatic effect of adding a very small quantity of polymers,
Yes.
a few parts per million. And it's known to be linked with the unwinding of the polymer in the turbulent fluid. So could you apply the same type of computation to the unwinding of polymers in a turbulent fluid?
That's a good question. I mean, what happens in the drag reduction is that you store some of the turbulent energy gets converted to elastic energy, and that suppresses the turbulent bursting of the walls, right? So,
Not only at the wall, also in the burst.
yeah, but I mean, it's the one of the walls, I think, which is responsible for the drag, basically. It's the ejection of blobs slow blobs from the wall to the center that need to be accelerated that leads to a lot of drag. Perhaps, that's a good question. I've never really thought about the connection between those two. I would have to think about it. I mean, the fact that there's no walls, there are walls, but there are no walls, if you know what I mean. So I'm not sure exactly what role that would play here. Yeah, I don't have such a good feeling for it. But it's a good thought.
So mucins have a lot of negative charges, and they love to rapidly spread themselves out and grab a lot of water. So would that kind of rapid expansion of the mucins contribute to this in some way?
I think maybe that's probably the answer, right? I think that the theory that I'm developing here is probably useful maybe at the beginning here, right?
Mm-hmm.
You get some thread out, and then once you have enough thread, maybe the mucins kind of all stick to the thread in some explosive way, and so things then become globally entangled, right? You can no longer think of these skeins as being isolated from each other, and the thread actually start catching on each other. So I think maybe the theory will turn out to be useful at the very beginning, just to tease out a little bit of thread, but after that, it's really going to be the mucins that will stick to the thread. But again, I'm not an expert on mucins, so I hesitate to make too many modeling steps to put this in. But if anybody, that's why I'm happy to give this talk here, because if anybody knows more about the role of mucins and how they could catalyze this, I would be very interested to hear it.
Okay, let's thank Jean-Luc again.